Welcome back to AP Calculus AB and BC. This is part 2. Last part was just a review of pre-calculus, but this part's going to be a preview of AP Calculus AB. So I'm going to talk about how to compute the derivative, some basic applications, and then how to compute the integral. We won't go into the applications of integral definitely because there are way too many of them, and some of them are advanced. So without further ado, let's start with derivatives. So we went over the pre-calculus version of derivatives last time. We said that a derivative is limit as h approaches 0 of f of x plus h minus f of x over h. This is the definition of a derivative, which is often written as d dx or f prime of x. But in pre-calculus and in early calculus, you would use this formula to calculate derivatives and the rate of change. But in once you actually learn about what the derivative is, you would use different formulas. So I'm going to introduce those formulas here. The first major one is the power rule. So the power rule basically states that if you have an expression in the form a times x to the power of n, so for example 2x cubed, let's take that as our example. The derivative of this would be a times n times x to the power of n minus 1. So in this example, we take the 3 down, so that'll become 6, and then x, and we reduce the exponent by 1. So this is the derivative of 6x. 6x squared is the derivative of 2x cubed. Now what's the derivative of 6x squared? You take the 2 down, 12, x, and reduce it by 1, you would just get 12x. And then what's the derivative of that? Well, there's an unknown or unseen 1 up here, so you take that down. 12, x to the power of 0, so this is 12. Derivative of that. This is 12x to the power of 0, so you take down the 0, and you get 0. So that's a long chain of derivatives. But some things we learned from this, the derivative of any constant is 0, and the derivative of a linear term is just the coefficient. So that's why we had 12x goes to 12, and 12 goes to 0. There are some other rules, but before we get into those, what does the derivative mean exactly? We said it's the instantaneous rate of change, or the slope of a tangent line at a point. So this, for example, would be the tangent line at this point, and the slope of that, the rise over run, is the derivative. So you can use the derivative to find the tangent line at that point using point-slope form. You know the slope, and you know at what point it's at, so you can use point-slope form to find the equation of the line. Now, why do we want to find the derivative? We'll get into a bit of that in the application section after this, but time to introduce the other derivative formulas. The sum rule. So when you have f of x plus g of x, the derivative of this is just you take the derivative of each one separately. Similarly, if you subtract them, you take the derivative of each one separately. What happens if you multiply f of x times g of x? Is it the same thing? You just get f prime of x times g prime of x? Well, not necessarily. In this case, we have a different formula, and it's a bit more complicated. You're going to get f of x times g prime of x plus f prime of x times g of x. That's the product rule for derivatives. There's also a similar one for division. If you have f of x over g of x, it's going to be g of x times f prime of x minus f of x times g prime of x. all over g of x squared. So let's go with an example. Let's say you're trying to find the derivative of the function negative x to the power 4 over 3x to the power of 6 plus 2x squared. Find the derivative of this. First, this is f of x, this is g of x, so f of x equals negative x to the power 4, while g of x equals 3x to the power of 6 plus 2x squared. So f prime of x, we can calculate to be, you bring down the 4, you get negative 4, and then x, you take 1 away from the exponent, you get negative 4x cubed. For g prime of x, we use the sum rule, so we just take each of them separately. So you take down the 6, you get 18, x to the power of 5, plus, you take down the 2, you get 4, x to the power of 1. So now, what was the formula? It was g of x times f prime of x. So that times that, minus f of x times g prime of x all over g of x squared. So that's going to take a lot of space and time to write out, but that's basically the process of how you would solve that problem. Okay, just a few more rules now. For trigonometric functions, how do you find the derivative of trigonometric functions? So sine x, the derivative of sine x is cosine x. The derivative of cosine x is negative sine x. The derivative of negative sine x is negative cosine x. And the derivative of negative cosine x is sine x. So it's a cycle. Whenever you take multiple derivatives of a function, in this case, if it's sine or cosine or negative cosine, you would end up with that same function after a few cycles. I won't go through the other trigonometric functions because it's all memorization, and it'll take too long to write them all here. It's not like a single formula that's really important. These are the most important trigonometric function formulas, but the others are good to know. Definitely good to know. Exponential functions, so the derivative of e to the power of x is e to the power of x. That's the definition of e to the power of x, actually. It's defined to be a function such that the derivative is the function itself. It's the only exponential function like that, though. There's a similar formula for the others. If it's a to the power of x, it's going to be a to the power of x times ln of a. And finally, the chain rule. If you have f of g of x, so this is about composition of functions, the derivative would be g prime of x times f prime of g of x. And those are basically all the rules we need to know for derivatives. Moving on to the applications of derivatives. The main one is L'Hopital's rule, which is about limits. So what if you come across this limit? What if it's something like x minus 2 over x squared minus 4? Limit as x approaches 2. You plug in 2, you get 0 in the numerator, 0 in the denominator. What do you do then? Well, you can always factor the denominator into x minus 2 times x plus 2, cancel out the x minus 2 and try again. But that's what you would do in pre-calculus. We didn't go over that because it's not as prevailing as the other concepts we needed to go over. But in calculus, there's another way of doing it, and that's the rule I mentioned earlier. You basically take the derivative of both the numerator and denominator and try it again. So take the derivative of the numerator, you get 1. Take the derivative of the denominator, you get 2x. You plug in 2, and you'll get 1 over 4, which is what you would get if you use the other method as well. Why is this helpful if we have the other method? Well, first of all, it's easier, and second of all, it's for limits such as this. What if you have limit as x approaches 0 of sine x over x? Well, you can't really factor anything out or use conjugates, which are usually the two methods we learn. In fact, in pre-calculus, you might learn this, and if you do, it's a special trigonometric limit that you need to memorize. But with calculus, we can prove what it's equal to. We just take the derivative of the numerator, which we said was cosine x, and the derivative of the denominator, which is 1, and it's just cosine x. And when you plug in 0 into cosine x, you get 1. So the answer is 1. So that's L'Hopital's rule. And another big application of derivatives is using them for graphs. So basically, when you have a function that you know the equation of, the first derivative of it determines the extrema, which I'll get to in a minute. And the second derivative determines the concavity. Extrema is basically maximum and minimum. So when it's equal to 0, when the first derivative is equal to 0, there's either a maximum or a minimum. And the reason why is because when you have a graph like this, when is the slope of the tangent line equal to 0? When it's a horizontal line, which means it's either a maximum or a minimum. So when the first derivative is positive, it's an increasing function, and when it's negative, it's decreasing function. Similarly, we have concavity. When the second derivative is positive, it's concave up, so sort of like an up-facing parabola. When it's negative, it's concave down. So that's another application of derivatives you should probably know. And that's basically it for derivatives. There's obviously a lot more, but for this preview, I think this is enough. Moving on to integrals. So integrals use the antiderivatives. Basically, you undo the derivative. So if you had 2x cubed as your function, the derivative, you would take down the 3, 6, and then do minus 1, so 6x squared. What's the antiderivative? There's a power rule for that too. If you start with a times x to the power of n, it becomes a over n plus 1 times x to the power of n plus 1. And let's try to take the derivative of this. You take down the n plus 1, which cancels with this in the denominator, and remove 1 from the exponent, and you get the exact same function. Because the n plus 1 cancels with this, 1 from the exponent becomes just x to the power of n, which is a times x to the power of n. So this is a proof of why this is the antiderivative version of the power rule. So let's plug that in here. If a is 2 and n is 3, so you'll get 2 times x to the power of 4 over 4, which simplifies down to x to the power of 4 over 2. So that's an example with the anti-power rule for antiderivatives. There are other formulas too. Obviously, the sum and difference formulas is the same as with derivatives. And then there's some we should memorize. So it's basically the inverse of that cycle I showed you for trigonometric functions. We said it's sine to cosine to negative cosine. In this case, it's sine to negative cosine, which goes to negative sine, which goes to cosine. So this the trigonometric loop I showed before went this way. This one goes that way. And there is a version of the chain rule for integrals, which I'll show you. It's called U substitution. So first, I'll give you an example for the chain rule for derivatives. Let's take the derivative of sine x squared. you would take the derivative of the inner function, which is 2x, times the derivative of the outer function, which is cosine x, and plug in that inner function in here, x squared. So that's basically the formula I showed before, except illustrated in an example. You take the derivative of the inner function times the derivative of the outer function of the inner function. Now, what about u substitution? Let's say it's an integral. This is the denotation of integral, by the way. It's a definite integral. There's definite and indefinite, but I won't go into it now because you don't really need to know that before you take calculus. This is just a preview of the main topics. So, but definite is when there's a given range you're trying to take the area of the curve under, and indefinite is just you're finding the antiderivative. So let's say it is sine x squared. Or let's say sine 2x, that would be easier. Sine 2x dx. What you would do is you say u is equal to 2x. So what is du? The derivative of u. It'll be equal to 2 dx. So what you would do is you would multiply this by 2 while dividing it by 2. So the 2's cancel off. But what you want to do is you want this 2 times dx to get du. So in this is replaced with sine, again, sine of u, because we replaced 2x with u, over 2. And then we have this 2 times dx, which we can replace with du. So now we just have a normal function, sine of u. We know that the antiderivative of that is negative cosine u. So it should be negative cosine u over 2 plus c. And I'll get into that, why that's important. And then you replace back u. You get 2x instead of u. So the integral of sine 2x is negative cosine 2x over 2. Now, why do we do that plus c? Whenever you have an indefinite integral, you want to add plus c to the end once you calculate the antiderivative. The reason why is because think of a function, sine x, for example. Let's say that was our antiderivative. Sine x plus 1, sine x plus 2. When you take the derivative of both of them, you still get the same function, cosine x. Cosine x is what we took the inverse of, or antiderivative of. So it's the integral dx. That's the symbol, and the function in the middle. So we took this to get that. But if you do sine x plus 50, for example, and take the derivative of that, the plus 50 will always go to 0. So it doesn't matter what constant is at the end, which is why you have to account for every possible case. So you just do plus c to denote that there is some constant. There could be some constant at the end, but we're not sure because the antiderivative like messes things up kind of. It doesn't let us know specifically what goes at the end. If you have a definite integral, it doesn't matter because you're trying to find the area under the curve, not what the actual antiderivative is. And in some cases, you'll be given a specific starting value. For example, when x is 0, the value of the function is 5. And using that, you'll find out what c is by plugging it into the function. And that's it for derivatives and integrals. I think we're done with this. It was rather short because we didn't go too much into detail for either of them. Just the overlying concepts, the main formulas, and things that you need to know for AP Calculus AB. And then we'll be back tomorrow with Part 3 AP Calculus BC and talk about a review of pre-calculus needed for BC. So, for example, polar functions, parametric functions, as well as AP Calculus BC itself. So that's it for today's video. See you next time.